All right. Can you all see this? Looking at the icon screen? All right. Thank you guys for working on this. Everybody got this done on time. Again, you guys are awesome. So you should have 2 points for making an honest effort to complete this, but I do want to go over the answers just to make sure that we're all on the same page. Okay. So first question in formative assessment number 2, linear versus nonlinear transformations. So the big difference is whether or not you are changing the information contained in a variable. A linear transformation does not, but a nonlinear transformation does. So let me see here. I've got some more in the waiting room. Get some folks in here. One of the answers I liked, let me try to see if I can remember who was that. Sarah, I think this might have been you, pointed out that if you were to plot two versions of a variable, one of which was the original and one of which had a linear transformation, you would see them on a straight line. So that was a good way of putting it, I thought. The purpose of a linear transformation is just to put a variable in a metric that is more interpretable. So for instance, converting the number correct into a percentage so that you get a sense of the absolute way that someone did on a test. Specific examples that we see in statistics, one is going to be centering, which is changing the mean of a variable so that it's closer to 0. We'll see that starting next week, I think. And also z-scoring, which is changing the metric of a variable so that the mean is 0 and the standard deviation is 1. Those are linear transformations just done for the sake of improving interpretation, or else to put variables that are on different scales onto the same scale so that their effects can be compared more readily. So everybody got that much. In terms of uses of a nonlinear transformation, something that I didn't ask about directly, but a lot of you contributed anyway. Thank you. The two examples I can think of would be to rein in extreme values. So for instance, a log transformation is used to take positively skewed data and squish in the tail. If you see in manuscripts people reporting that they reflected a variable and then did either a log transformation or maybe a square root transformation, that means the variable was negatively skewed to begin with, and you can't take a log to solve that, but you can after you reflect it, which would mean to basically make the variable values go backwards in terms of what more means. The other instance besides reeling in extreme values that you might use a nonlinear transformation for is to extend the boundaries of a variable that has closed intervals that it can't go past. So for instance, in our correlation effect size, it's bounded between -1 and 1. And in order to compute a confidence interval for an R, we need to convert it to a unbounded version, which is the R to Z transformation, and then back translate into R. So you'll see that come up in advanced statistics dealing with boundaries in predicting outcomes that are either categorical or that have boundaries such as proportions. Nonlinear transformations will be used to solve that problem. But okay, any questions on that much? Nope. Okay. Number 2, hypothesis. So this one, everybody sort of has, I think.
Lisa, I had a question.
Yeah, please
Sorry.
go ahead.
Um, can you explain to me again, like why when we have that correlation, I understand why it's bounded between -1 and 1,
Hmm.
but I can't, I still can't see why you need to extend it, the boundaries.
Let me pull up a picture. 1 second here. This picture on slide 20 of lecture 2, it's coming up here just a second. So this is an example of what the sampling distribution would look like for a correlation on the bottom that's 0.8 in the population. And
Okay.
so if you look at this row of the table, can you see what I've highlighted here?
Yes.
Okay, so if you have 10 people and you are drawing samples of these 10 people from the population repeatedly, like I did here, I did this 1,000 times. The average correlation that was in each sample of 10 people was 0.77. However, the variability across what those correlations ended up being the standard deviation conveys that variability, and it was 0.15, meaning that any one sample of 10 people, how far off that correlation was from the average was 0.15.
Okay.
So if you were to take that 0.15 and use it as a standard error in a formula to compute a confidence interval, the confidence interval is always what you got is the middle, so the 0.77 here, and then about 2 standard errors on either side of it. Well, if I go 0.77 plus 2 times 0.15, that gets me past a 1, which is the highest that a correlation can go.
Oh, okay.
So the
Okay. Now,
interval around it exceeds the possible boundary. And
okay.
so that can't work, right?
Right.
Like that can't
Mhm.
happen. So what would have to happen instead is that R of 0.77, the mean, would be translated into a Z value. That's the Fisher R to Z transformation. You
Okay.
would then compute the confidence interval in Z values because Z can keep going, and then back translate those Z's into R's that would form the boundaries of the R confidence interval. And what's going to happen is that the interval is not going to be symmetric anymore because it can't go past 1. So it may have
Mhm.
a wider part on the negative side than on the positive side.
Okay.
Okay, does that help a little bit?
Yeah, no, now I remember. I remember you saying that before. Yeah, I just forgot. Yeah,
Well,
thank you.
you're not
Yeah,
expected to remember every single thing I've said for the past 6 weeks. That's why we do reviews, right? This is
yeah.
great. Another time in which the same problem would show up is if you're trying to put a confidence interval around the mean of a binary variable. So, for
Okay.
instance, if you have a mean that's like 0.95, where 95% of your sample got a 1 and 5% got a 0, a confidence interval around that in a small sample could make it go past 1. And you can't
Okay.
have a mean past 1 in a binary variable of 0 or 1 values. So, anytime that you have a statistic that has a boundary, right? This is a nonlinear transformation of something is likely to be involved in order to back translate that statistic's confidence interval into something that respects the boundary.
Got it. Thank you.
Sure. Thanks for asking. Okay, get back to that. So any other questions on number 1 before we head into null hypothesis significance testing? Okay, then this one. So in this, what is the null? A lot of you said the null is 0. That is true sometimes, but not always. The definition of a null is whatever expected means in the context of the test that you're asking for. So we've seen a couple examples of this. We started off with univariate analyses, testing whether or not a sample mean is different enough from a population mean, where the population mean would be the null in that example. Like, what should it be? Okay, the mean age for graduate students in homework 1, for instance, was supposed to be 28. And your sample means were all generated, by the way, to have positive skewness. And the other one we did was a undergraduate GPA was generated to have negative skewness with a mean of 3.6 as the benchmark. In the context of correlations, for bivariate analyses, the null hypothesis is often that there is no association, meaning an R of 0. But more generally, the null is just whatever is expected. Wherever you're putting, your line in the sand, like what is the basis for my test? And you're comparing what you got relative to that expected value. Do you remember what it's called if your null hypothesis is not 0? It's a tongue twister. A non-nil null. Yeah, I can't make this stuff up. Non-nil null is what it would be called. But for instance, you may be in a situation where you're reviewing studies that are focused on a common theme, say the effectiveness of a certain type of therapeutic technique. And there's a bunch of different studies that have examined the same phenomenon. And let's say that previous studies have generated a tendency towards, say, therapeutic alliance being higher in people who do more of the activities that they're supposed to. So participation results in better outcomes. And you may have, across all of those studies, say, an average correlation of about zero point 0.3. Well, if you want to compare your new study results to what's currently in the literature, you could set that general zero point 0.3 expectation as your null and compare your result relative to that. The formulas change a little bit because you have to adjust for the fact that zero point 0.3 is your baseline, but the premise is still the same and the software will do it for you. You would just have to specify that you want zero point 0.3 as the null instead of 0. It would still be tested using a t-distribution, the same as any other correlation. So given the null is what you expect, then the question is, how discrepant is what you got in your sample relative to that expected null value? And we're trying to make a black and white distinction as to whether or not what you found is within expected sampling fluctuation. So you may hear the term sampling error to go with that. Those words kind of mean the same thing. The idea that if I have a population and I draw samples from it, the samples are not going to agree with each other 100% in the results that they give. They're going to wiggle around, what the true value is. And the question is, how much wiggle is acceptable? So you decide these things ahead of time. How much wiggle is acceptable translates into what percentage of the time would you find what you found relative to the null. So for instance, if we say 95% of the time is our boundaries for what expected wiggle would be, and then 5% is outside, that 5% is called alpha. So given that we've decided on whatever percentage is outside the boundaries and whether or not we're willing to accept a result that's too high or too low, that's a two-tailed test, which is what we're always going to do in this class, then we compare what we found relative to the null. So if we have a test statistic, so a t-value, a z-value, a chi-square, or f, which you haven't met yet, but who's coming, if that test statistic is past the critical value, meaning that it's into unexpected territory, if the p-value is less than the alpha that you chose. A point of clarification, by the way, it's less than. If the p-value is equal to or greater than, that is a retain the null situation. So less than 0.05 is the strict definition. So if you set up 0.05 as your alpha level where unexpected begins and your p-value that goes with your test statistic is less than 0.05, that is a reject, meaning that it is unlikely, it would happen less than 5% of the time that you find a sample result as extreme as what you found relative to your expected benchmark of a null hypothesis. So the null is the anchor point, and you're saying, where did you land relative to that null? How far away are you? And that's what the job of a test statistic is to tell you. The test statistic is a way of locating your result relative to the null in a standardized space, where a test statistic value for t or z, for instance, of about 2-ish in absolute value, usually corresponds to the 0.05 benchmark. It's going to be higher in smaller samples with t. Z is the one that ignores sample size, and it's 1.96 is the critical value that goes with Z at an alpha of 0.05.
Can you repeat that again? Yeah, sorry.
Oh,
I think we're saying the same thing. Can you repeat that again?
I would love to. Okay, so yeah, just Mariana just got your note. Cool. Okay. Yes. Which part or all of it?
I needed from where you started saying job of the test statistic. I don't know if Deb, did you need something else?
Yeah, I was wondering when you said if you could just describe that p-value is equal or greater than
Okay.
what you were.
I think
Okay.
P was before that. So,
Yeah.
okay. Yeah, can you tell I don't have a script? It's sort of like stream of consciousness here that you're getting. So I'm happy to try to engage in internal consistency in what I'm trying to say, if I say it over again correctly. Okay, so the retain versus reject decision, that's based on your p-value. Ahead of time, you decide what your cutoff's going to be. That cutoff is called alpha. So if you say alpha of 0.05, then your p-value needs to be less than 0.05 for it to be significant. If your p-value is equal to 0.05 or greater, that is not significant. So significant means unexpected, aberrant, Non-significant means within expected sampling fluctuation. Okay, let's see, there's Deborah. Is that better, Deborah? Okay, that part's good. Okay, now what does the test statistic tell you? So where does the p-value come from? The p-value comes from the location of your test statistic. So a test statistic is going to be one of four letters: T, Z, chi-square, or F. I guess chi is a square, but that's a Greek letter. The role of a test statistic is to locate your result relative to the null onto a standardized scale. So for the test statistics that you've seen so far, Z and T, the center of where 0 is on those corresponds to what the null is. The standard deviation, so how far off the null, is given by your standard error. So the standard error is your how far off on average would the sample version of this statistic be from the population value it's supposed to be. And we talked about that in reference to a mean. You can also have standard errors in reference to variances. You can have them for medians. You can have them for correlations. You can have them for any statistic that you can compute for a sample. What goes with it is an index of imprecision. And in general, standard errors are higher if there's more variability in the variable. So if people are more spread out from each other within the sample, and standard error is also going to be higher if n is smaller. So given a standard error and given your null hypothesis, you know what your result corresponds to. So if you have T or Z where the center is 0, your test statistic is a standardized how far off from the null is what you found, where 2 corresponds to an alpha of 0.05. If it's a T and you have fewer people, it needs to be a little bit higher than 2. The software knows what the exact critical value is, and it gives you the exact p-value anyway. So T gets hidden from you some of the time because T is just a way to get to the p-value that goes with it. Okay, so the job of a test statistic more generally is to standardize what you found relative to what you thought you should find, which is the null hypothesis. That brings up another issue. Do you want to reject the null or not? It depends. In almost every case that you will see with respect to measures of association, so are two variables related? Are two variables still related after considering a third variable, for instance? Questions like that. Generally speaking, the researcher wants to reject the null that there is no association. The reason they bothered to collect those variables in the first place was to see how well associated they are. But that's not always the case. So I can think of one example that we've already talked about in which you don't want to reject the null. If you want to claim that your sample is representative of the population it came from, right? So if you say that your sample should be 30% in-service teachers and 70% whatever the opposite is. This is an example from my other class. In-service versus out-service. What's the other half of that? Anyone? No? Please don't make me the education expert in the room. Bad things happen. But I just know that I was reading several of my students' homeworks describing teacher-related data, and it was in-service versus something else. But point being, let's say that it has to be 30% of your teachers are pre-service. Okay, thank you. That works. I have no idea what these things mean, but I'm going to pretend. So 30% of your sample needs to be in-service teacher so that your sample reflects the population of blah, blah, blah school district, for instance. You want to be able to say that it's reflective, right? That your sample is good, that you can generalize from it. So you want your sample mean to be not different than the expected mean. You want to retain the null in that case. Now, the easiest way to do that is to have a very small sample. This is something that we're going to be talking about to lack statistical power. The smaller your sample, the harder it is to reject the null. The harder it is to find something to be different than expected. So it's not necessarily that you want to reject the null or that you don't want to. It depends on the context. There are other situations in statistics where the null hypothesis is that you've adequately represented the patterns in the data with the model that you have, and you want that to be true in those cases. So null is a benchmark. You It tends to be you want to reject it if the benchmark is no association and you're trying to find associations. But there are other examples of testing the null in which you would want to retain, not accept, but retain. Okay, that's a lot of words on question 2. Does that help? Any of that you want to hear again or hear differently? Okay. Last one then, measures association. So what have we learned and what do we do with them? These are somewhat confusing because it gets hard to keep track of what is an effect size versus a test statistic. And I was all set to make up a table, and then Nikki, is that who did it? Where are you? Think that was her. I just read all of your assignments, by the way, like back to back. So I'm forgive me if I mischaracterize any of your work, but she made a table, so I was going to make the same table because we know some of them and we don't know others. So the easiest way to organize this, I think, is I'm going to make a table. I can post this for you after I'm done. This is me like writing on the board, by the way, if we were, back in the real world. Although with my handwriting and the distance of the room, I would probably do better with Excel anyway. So we'll do variable types as one column here. And then name of the association. We'll make that one. And then we'll do effect size and test statistic. There we go. Those are our broad categories. So we did, as our first pass at this, quant and quant. Okay, what goes here? Pearson or Spearman? Yeah, so I'm going to do Pearson first. So we call this Pearson correlation. That's what the technique is called. Like in your results section, you would say, I used Pearson correlation to examine the association between this and this. What's the effect size that comes out of it? It's a letter. Yeah, R. R, and I'll put from -1 to 1. And how do I know if that R is significantly different from my null hypothesis of, say, 0? Which test statistic? Yeah, this is a T. So yeah. And the only thing that I need to know to get from R to T is sample size. T is a function of the R value that you found and the sample size that you have. We will do, as a second example of this, quant and quant. When might you do Spearman correlation? When might you choose a Spearman correlation instead of a Pearson correlation if you're talking about two quantitative variables? Farhan says outliers. Indeed, what are outliers? I called them randos last week, but more generally, they're extreme values. Yeah, so if you have a distribution that's skewed because you've got people that are way far away from the rest of the people, those extreme values can drag the correlation slope more. So some people count more essentially in dictating what the correlation is. If you want to demonstrate evidence that those people are not unilaterally responsible for your association, you would do potentially Spearman instead, but what's the difference between these two things? Do you remember? Nope. Thank you for your honesty. That's why we're reviewing. Spearman ranks, yeah. So Pearson correlation uses the two variables as is, and it first deviates each case from the mean, and then you square those deviations, sum them up, and you would do the same thing for the other variable. So basically, how far off from the mean are the two variables forms the basis of what's covariance. And then once you divide by the standard deviations of the variables, that puts it in the correlation metric. But you're using the original data is the point. In Spearman correlation, you first rank order the data. So the lowest value is 1. The next lowest value is 2. The next lowest value is 3. And it doesn't matter if they're apart by 10 or they're apart by 1. The next one is 3. The next one is 4. So it essentially makes it ordinal. It destroys the distances between them, so it compresses everything back together. And then it does a Pearson correlation on those rank ordered values. So it's the data going in that make the difference between Pearson and Spearman. Pearson is original data, Spearman is rank ordered. But in terms of this part, it's exactly the same. You end up with an R-type statistic, or what you may call rho to differentiate it. Spearman's rho is what it's sometimes called. And your test statistic is still T. Okay, how are we doing so far? Good. All right. What about binary and quant? You could do either Pearson or Spearman, with the difference being how you're talking about the quant part. Point by serial is what it is called, but it's the same damn thing as Pearson. Point by serial is just a synonym for this particular thing. So either way, I'm going to put U of n R as your effect size, and you test that effect size for significance using T. Binary and binary. This one actually has two different answers, only one of which we've talked about so far. Could I do Pearson here? I can, but it will be limited. Yeah. Pearson, I'm going to put limited here. The issue with binary data is that to the extent that the two variables do not both have 50-50 splits in their 0, 1 values, the maximum Pearson correlation that you get is going to be under 1. So you can use Pearson, it's just not the best way to index the relationship. But if you do that, then the rest of these follow suit. What about ordinal and any of the others?
The chi-square?
Chi-square is one way to do it we haven't talked about. What's another one? Yeah, you can do Spearman for this. Yep. That can be a Spearman one with these. Now anything that is involving categorical and categorical. So I'll say cat and cat. So that could be binary and binary, binary and ordinal, binary and nominal, nominal and nominal, etc. Any combination of there. This is the one that we haven't talked about. And you would call this a chi-square analysis. Or sometimes you might say contingency table analysis, something like that. Now this one is different because you don't get an effect size directly out of it. We haven't talked about this one yet. But what you get directly out of it is the chi-square test statistic. That's it. That's what you get the name, the chi-square test. You get a test statistic directly. And then you have to decide what kind of effect size you want to go with it. So that's the one that we haven't done yet. Here's another one that we haven't done yet. Let's say nominal and quant. What do you think about that one? This is a trick question. Here's my answer. Next week. Actually, probably 2 weeks. I'll rephrase that. Need a model for that one. Take an advanced stat class? No. Stay with me for 2 more weeks and we'll get there. Yeah, where the issues start to come in is that any variable that needs more than one mean to summarize it, the measure of association that you need has to take into account both of those means, or more than all of the means in question. It's hard to explain this in an abstract way, but we'll get to chi-square analysis and that will make more sense. But that's what makes nominal different, is that in nominal you have more than one category and you would need to know the frequency in each category. You can't just put them on a line or something like that the way that you can with a quantitative variable because they're not numbers. So these ones are the ones that are still yet to come. Okay. And there are other ones that I mentioned that are the better way of indexing relationships for variables that have range restriction. Binary and binary is tetrachoric, and ordinal with ordinal would be polychoric as an example. Those you do have to sign up for an advanced stats class to come back to, but we'll get there. Okay, so questions on this, and I will post this after class today. Okay. Alrighty then. So put that down, put this down, and then we can start talking about chi-square, the thing that we haven't talked about yet. How's that sound? Why not? Yes. So let me find that. We started on that at the end last week. Slide 29, that's where we're going to pick up from. This is still lecture 2. This thing. So this is an example of binary versus binary, and trying to get an association between one's membership in a category of a variable with their membership in the category of another variable. This example was taken from your textbook, and it is looking at real-world data. One of the variables is the defendant's race in various court cases, whether they are white versus non-white, so they're collapsing into 2 categories for the purposes of this analysis. And the other variable is whether or not they were given the death sentence for their various crime. And this table is showing several pieces of information simultaneously. So out here, the totals, for instance, 284 is the total number of non-white people included in the analysis versus 541 white people. So these are what's known as the margins, or a marginal result. So that's just describing race univariately without respect to the other variable. Likewise, the totals that are given down here across the rows are for death sentence. So 66 people received a death sentence, 759 did not. That's marginally, just univariately for the death sentence variable. And then inside the table here, these are known as cells. cells that are combinations of particular values on one variable with particular values on another. And these contingency tables like this are generally organized without respect to order of the variables. So like there's no ordering that's necessarily implied by the rows versus the columns. So these can be used for binary variables, ordinal variables, or nominal variables. The values that are given in each of the cells, like the 33 here and the 33 here, this is what happened. So these are the actual frequencies observed. So there were 33 non-white people who were given the death sentence, and there were 33 white people given the death sentence, and 251 and 508. So that's what happened. In order to know whether or not there's an association between these variables, is it the case that white people are given the death sentence less often, for instance? That might be your hypothesis. We have to know what is expected. And what is expected is generated from the margins, these totals out here. So inside each of these cells in parentheses, these are what's known as expected frequencies or expected cell counts, and they are each computed as the number of people in that row, so the 284 for instance, times the number of people in the column, the 66 for this cell, divided by the total. So for instance, for this cell right here, where that 22.7 came from is the total for the row times the total for the column divided by the grand total. So if these variables had nothing to do with each other, then I should have seen about 23 people in that combination of non-white people who were given a death sentence. Likewise, if these variables had nothing to do with each other, then I should have seen about 43 white people who were given a death sentence. And we can compare the actual to the expected as our index of whether or not these things are associated. So the basis of chi-square is to literally do that comparison. For each cell, how far off is what happened for real versus what should have happened based on the margins, based on the total for the column and the total for the row. And you can do this type of analysis readily in SAS Proc Freak, which you already have seen, and Stata, it's tab 2, along with an extra thing, CS for effect sizes that go with it. So Pearson's chi-square is a summary across all the cells in the table of how far off each of the cells was. So the formula is to go across all the cells here, so that's what the sigma here is doing, and it's observed minus expected. So for instance, I got 33, I should have got 22. I square that, square so that the positives and negatives don't cancel each other out, and divide by what was expected. So this first quantity here gives me an offness for the first cell, the second cell, the third cell, the fourth cell. And altogether, if I do the math, it works out to be a chi-square value of 7.7. And the question then is, okay, what the hell is that? Chi-square is a test statistic, and it is compared to a chi-square distribution. What makes chi-square different is that it is in a squared metric. So Z and T are in an unsquared metric. They can take on positive or negative values. Chi-square is in a squared metric, so it can only take on positive values. So you can't look at the test statistic and know what type of association it is. So like when we did a correlation, we immediately got an R that was positive or an R that was negative. And the t-value that goes with the r was either positive or negative. So I know right away that if it's positive, then as x goes up, y goes up, and if it's negative, as x goes up, y goes down. There's none of that here. I got a 7. What the hell do I do with that? First thing I got to do is figure out whether or not a 7 is unexpected. So the reference for unexpected is the chi-square distribution. And the only thing that we need to know is how many degrees of freedom we have with respect to this table. Now, this is a new kind of degrees of freedom. It's what's known as degrees of freedom in the numerator. It's how many cells you have to know to figure out the rest of them. So for instance, if I know one of these cells, if I know this 508, well, because I know the total is 759, I know that this other one has to be 251. And if I know this is 251, given that the total is 284, I know this one had to be 33. As another example, if you're out to dinner with 3 of your friends and they come up and say, okay, who had the veggie burger? Who had the pasta? Who had the salad? Right? The last plate, you shouldn't need to ask, right? It should go to the last person who doesn't have food. Degrees of freedom 1 on that. So in this case, I only need to know one cell and I can figure out the other 3. That's because there are only 2 possible values for each of the variables. What's not included here is sample size. So chi-square only pays attention to how many cells you had to know to figure out the rest, degrees of freedom numerator. It does not pay attention to degrees of freedom denominator, the number of people. So here's a picture of what chi-square looks like. It's funky. It only has positive values, and the shape of it depends on the numerator degrees of freedom. In this case, it would be how many cells you have to know to be able to figure out all the rest of them. So this yellow line right here is what the chi-square distribution looks like for a 2 by 2 table. The critical value is 3.84, which is right here. This is the point where unexpected begins. So there's no other tail on the negative side. If there's an association, it shows up as the amount of chi-square, not as a sign of chi-square. It's always going to be positive. Our obtained value was 7.71, which is out here. So if we follow this yellow line, 3.84 is the point where 5% begins. So a critical value of 3.84 is the dividing line where unexpected starts, where the whole tail to this side, excuse me, I'm going the wrong way, is unexpected territory. So you have to know what your degrees of freedom are to know what your critical value is. So if we look at, say, for green, this is what it would look like if there are 2 degrees of freedom, meaning you have to know 2 cells. Degrees of freedom is the number of rows minus 1 times the number of columns minus 1. And then we get into this teal color and into blue and then into purple and so forth. So what we can say based on these results is that because our obtained chi-square is over here, the 7 whatever, and it's past the critical point where alpha of 0.05 begins, then we reject the null. These things are associated. And the exact p-value that goes with this is 0.005. So if these 2 variables were unrelated, if your race had nothing to do with whether or not you were given a death sentence, then we would see this type of association, this pattern of association, less than 0.5% of the time. So these 2 cells have nothing to do with each other is our null hypothesis. That corresponds to a chi-square value with value that's the same as the degrees of freedom. So a chi-square value of 1 is essentially the null hypothesis if you have 1 degree of freedom. A chi-square of 2 is the null hypothesis. It's kind of screwy. But just keep in mind that chi-square is always positive, and where significant begins is based on your degrees of freedom for the numerator, how many cells you needed to know to be able to fill out the rest of the table. So then the question is, what do we do with this? It's a significant result. These things are associated, but how? That part we don't know yet. And this is where, if you have a 2 by 2 table, all you need to know is one of the cells and you can figure out the rest. So if I look at this pattern right here, the 508 versus the 497, there were more white people not given a death sentence than expected. That's my pattern. So not only is there an association that would be found less than 5% of the time if there were no association in the population, but the pattern of the association is such that being white is more associated with not having a death penalty than expected. And you can say it backwards too. You could say that being not white is expected to is you have a death penalty decision more than expected. So this is starting to map onto the language of correlation a little bit. It gets very tricky with binary data, but in fact, we can convert this chi-square into an R for an effect size. So here's my attempt at describing the pattern of the association more generally. You can refer to the columns as your baseline or the rows as your baseline, but either way. So in this case, we can also calculate a Pearson correlation for the same association. Because we said that a few minutes ago, right? Binary and binary on our table. Let me find my table again. Where is it? Binary and binary. So I could compute a Pearson correlation for these two variables, or I could compute a Pearson chi-square. There is a mapping of one to the other. I'll show you the formula in just a minute. The difference in terms of how they're tested, though, has to do with whether or not denominator degrees of freedom are used. Pearson correlation pays attention to denominator degrees of freedom by using t, whereas Pearson chi-square does not. So in practice, for small samples, the significance values that go with them can disagree, but you can talk about effect size for correlation using an R metric. And I'll show you that in just a minute. Okay. Now, what about this table? Here's an example of an ordinal with a binary. So the rows on slide 33 here have to do with the number of types of child abuse that someone has said happened to them, 0, 1, 2, or 3 to 4, and then whether or not they were abused as an adult. So the null hypothesis that's being tested in this example is no association. If I go through and compare the observed cells in each of these 8 in this case to the expected, I come up with my chi-square and it works out to be about 30. Well, in this case, I need to know 3 cells in order to figure out the rest. The formula for how many cells you need to know, numerator, degrees of freedom, is the number of rows times the number of columns. That's where that comes from. But I need to know, say, 3 of the cells. If I know these 3 right here, I can figure out the 4th, and then I can figure out this whole section based on the margins. So a chi-square of 30 relative to my critical value of 7.82 means that I would reject the null. But what's the pattern? It could be that people who were not abused as an adult there's more of them that were expected that were not abused as a child. It could also be something over here that people who were not abused as an adult have fewer of them who were abused as a child. I could come up and go through here and list a whole bunch of these, right? The problem with a 3 degree of freedom test is that there are different ways these variables can be associated with each other if you look at the specific pairings. It's impossible to nail down like which pattern is the one that's creating the significant result. So the 30 being significant is somewhat dissatisfying. It doesn't tell me very specifically how these variables are related to each other. And to be able to get that information, you can break up this table into 2x2 combinations and test each of those to get a sense of more specifically what the association is, or you can fit a model to it, and that is a come back in a few semesters for the generalized linear modeling class, which is when we predict categorical outcomes. So this starts to break down in terms of its utility in situations in which you have these multiple categories and therefore there's multiple types of associations. So nominal is not as useful. Okay, before I jump into more stuff, how are we doing? So if we go back to my table here we go, cat and cat. We haven't filled in this cell yet. If I have some combination of a categorical variable with another categorical variable, nominal with ordinal, nominal with binary, ordinal with nominal, etc., I can compute a chi-square test statistic, and that can tell me whether or not I have an association. But that chi-square statistic is partially reflective of my sample size. The more people I have, the higher my chi-square. The easier it is to declare my association significant. So I need an effect size. There are different options that are going to be more or less useful depending on the context. So we'll get to those here in just a second. If you're interested in these sorts of categorical data analyses and effect sizes, there is a classic textbook. Agresti is the author, Categorical Data Analysis. The library has it. Send me an email if you want a link and I can send you some suggested chapters that will better articulate this stuff. This is just a real quick overview to give you the right words to Google if you need to do this in more detail later in your life. So we're using chi-square to test significance without paying attention to sample size. So in small samples, we know this is probably not going to be a great approximation in the same way that Z didn't work very well with small samples and we use T instead. So there are various solutions that have been developed that better, I would say, offer more correct test statistics when you have smaller samples. These are what's known as exact tests. There's other things that you will see, versions of this observed versus expected that go by different names. There are corrections to these chi-square contingency table analyses if certain categories have different base rates. So kappa, for instance, I think someone asked me about that. Cohen's kappa. It's often used for association in the context of inter-rater reliability, and that builds in basically a penalty if certain categories are just more frequent, and that's why it looks like you agreed more. So it takes into account the base rates and the margins in computing the measures of association. The effect sizes that we can get. So if you have a binary by binary contingency table, a 2 by 2, you can get your R effect size by taking that obtained chi-square test statistic, dividing by sample size, and then taking the square root. The R will be unsigned, like it's going to be positive because it's the square root of something, but it is an effect size measure. So one of the things that I'm asking you to do in your homework too is to compute both a chi-square test and a Pearson correlation between two binary variables so you can see how they're telling you about the same information. More generally, you can get an R effect size out of any t-test statistic. So if you're in a situation where an author, for instance, gave you a t-value and a p-value and they didn't give you an R, you can get one back. So we'll see that. And then here's a couple more that show up with contingency tables in particular. Risk ratios and odds ratios. And these are ways of expressing likelihood of certain cell combinations relative to the others. So for instance, here's another 2 by 2 table where we're looking at taking aspirin versus placebo in the context of preventing heart attacks. So most of the people, fortunately, in this sample did not have a heart attack. And the question is, how effective is aspirin relative to placebo in preventing heart attacks? Well, if I go through just the numbers here, I get a chi-square that's 25. So with 1 degree of freedom, meaning I only need to know one cell in the table to get the rest, that's significant. But to express how big of an association that is, then I can do that a couple different ways by using the numbers within the table. So one thing that you can compute is what's known as risk, and that is what happened. So 104 people taking aspirin, for instance, had a heart attack relative to the total number of people taking aspirin. So if you took aspirin, your risk of having a heart attack was only 0.94%, whereas if you took the placebo, 189 people had a heart attack out of 11,034, their risk is 1.71%. So either way, the risk is small, but it looks to be smaller if you take aspirin. And so if you take those two risks and form a ratio of them, then that ratio is interpreted as an effect size. So a 1.8 relative risk. So without aspirin, your risk of having a heart attack if you take placebo instead is 1.8 times greater. So this shows up a lot in epidemiology, public health, those kinds of studies. If you're doing medical studies where the outcome is like death or disease acquisition, something like that, where it's a cut and dry, these sorts of risk effect sizes are very commonly used. One that's related to relative risk but uses slightly different values in the computation is odds ratios. In this case, rather than having the event over the total, it's the event over not the event. So the odds, given that you took aspirin, of having a heart attack is 104 over the not having a heart attack, which is the 0.95, whereas the odds if you took placebo is 1.74. And again, dividing these forms a ratio. I'm going to be honest with you, odds ratios are really super common. I hate them. I hate them with the fire of 1,000 suns. Do you know why I hate them? Because they're a screwy metric. So in the metric of relative risk or the metric of odds, a ratio of 1 means that your two variables are unrelated. Your odds are just the same if you took aspirin, whereas if you didn't take aspirin. If something is related in a positive way, then a positive relationship goes from 1 to positive infinity. That's what scale the effect size can be. But if it's a negative relationship, that entire relationship is shoved between the interval of 1 and 0. So 0 to 1 means a negative relationship. 1 to positive infinity means a positive relationship. It's asymmetric and I can't handle it. I just can't. So I'm teaching you odds ratios because everyone loves them and reports them. I hate them. So there's my 2 cents. I can't handle it. I like logits better. So if you stick with me, you'll learn what a logit is, which is the log of the odds of the probability of a 1, which is a symmetric thing that starts at 0. Thank you, Kaylin. She's very emphatic. You love logits too? Yeah, the logit is where it's at. So stick with me and we'll talk about logits, but that's much better. I hate odds, but here you go. And these, like every other number, are things you can ask your software to spit out for you. So all of these things are options within ProcFreak or Tabulate and Stata to get all of these sorts of table relative risk thingies. And note that that's not a coincidence that these examples are using a 2x2 table. Because if I wanted to talk about odds or relative risk for, say, this example right here on slide 33, there would be more than one set of odds, right? I'd have to talk about the risk of being abused as an adult for somebody who checked 0 versus 1, 1 versus 2, 2 versus 3, 0 versus 2, and so forth, right? There's a whole bunch of different odds that you could get out of this table. So it's this one table really implies a whole set of results. That's when it gets harder to talk about effect size because you're really talking about multiple effect sizes potentially at the same time. Okay, I think that's what I was going to say about that. Okay, do you want to see how to do it? Good news, you already know how to do it. It's just an extra set of options. So let's pop open here example 2 and head on down to the part that we haven't seen. We did correlations, Pearson's, Spearman, them for ordinal. Talked about that last time. Here we go. This is page 9 of example 2. And this is, I believe, section 2 of homework 2. Does that sound right? It's the last part of homework 2, I can tell you that much. So you should be able to do all of that after today. So I have 2 variables. I just used 2 example variables from the data set. It's not a terribly interesting analysis, but it works for the point of demonstration. The same general social survey data where I am looking at whether or not there's an association of the binary gender of the respondent with a binary status of whether they're married or not. So this might be a sample representativeness kind of thing. Like I want to make sure that I have equal proportions of men who are unmarried, men who are married, women who are married, and women who are unmarried, etc. And these are all binary because that's the world in which the General Social Survey was collected back in 2012 or whenever these data were acquired. So in SAS, we're using our friend ProcFreak. Remember what freak stands for?
Frequency.
Yeah, frequencies. So anytime that you need univariate summary information or bivariate association information for categorical variables, it's proc freak is your friend. Freak is your friend. How's that for a mnemonic? Freak is your friend if they're categories, where you want frequencies, percentages, expected frequencies, and that kind of thing. So in SAS, we always have to tell it the name of our data set as the first thing. Table is where we list the variables. And here's the new thing right there, an asterisk. When you list more than one variable concatenated with an asterisk, what you're asking for is all possible combinations to be given to you. You can do 3 variables separated by 2 asterisks if you want to, and it would make a 3-way table. So I'm getting the contingency table for these 2 variables. It figures out how many rows and columns it takes. So there's nothing different you have to do if these were binary variables versus nominal variables or what have you. I am suppressing some of the additional information, the row and column totals and percentages, so that the output is a little less overwhelming. Alpha equals 0.05 refers to my hypothesis test. Chi-square is asking for me to get the Pearson chi-square, and expected means please give me the expected frequencies so that I can answer those questions on my homework. Homework question, cough, cough. Stata folks, yours looks very similar, except that it's the word tabulate, which is like make me a table. You don't need to put anything between the 2 variables. Just listing them both there gives you the contingency table of all possible combinations. And if you have the keyword option cell, then it gives you the cells as well as the margins. And chi-square and expected frequencies is a separate command that's known as tab2 for 2-way. Chi2 is the equivalent of chi-square, and the option for expected gives you expected frequencies, the same as in SAS. So let's see what we get. So going back to the SAS output on page 9, we have 197 men who claim to be unmarried and 166 men who claim to be married. And okay, that's what happened. What should have happened? The second row is the expected frequency. So based on the number of men that answered the survey and the number of people who were unmarried, based on those combinations, I should have had 196.3 men fall into that combination. And in reality, I had 197. So pretty darn close to expected, just a little bit more of a men. I'm not sure how to think about fractional people, but yeah, the fact that these are fractions should clue you into the fact that there's some sort of expectation. I did not have 196.3 people in that category. And then the percentages are given to you underneath here. So if I take how far off for each of my cells, observed minus expected squared, divide by expected, add that up across all 4 cells, I end up with my chi-square value right here. So it gives you all kinds of measures of association. Regular old flavored chi-square is the one that we're going to pay attention to. And so the value of that test statistic for this contingency table is 0.0097. Is that good? Is that a lot? Well, prob, next to that, can you guess what that is? Prob, what does prob stand for?
Probability.
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 Yeah, that's my p-value. So p-value looks a little different depending on what it's referring to. Sometimes it's called prob, sometimes it's called PR greater than absolute value as something else. But right here, this is a p-value of 0.92. In other words, if marital status and binary gender were unrelated, then I would see a discrepancy between expected and observed this large or larger 92% of the time. So is my association significant according to this result? No. No, this is telling me that, yeah, this is well within expected sampling fluctuation, that I could get 197 people in this category when I was only supposed to get 196.34. Well within expected territory. There is no association between these variables. Retain the null hypothesis. It looks like I don't have an oversampling of, say, unmarried men. To get an effect size for this chi-square statistic, so I know it's significant, I don't yet know my effect size. There's actually 2 different ways you can get to it in SAS. One is right here, and the other is down here under proc core. So I'm asking for a Pearson correlation between my 2 binary variables, and the Pearson correlation that it generated for me, my effect size, is 0.00363. That number was also found up here as a phi coefficient. Phi correlation is the same thing as a Pearson correlation. It's just a different name. So I have a positive correlation between these 2 things of 0.004, which if I compare that correlation, if I translate that into a t, the probability that goes with that t is 0.92. So very, very close to what I found up here. Just a difference in whether the reference test statistic is a chi-square that does not pay attention to sample size or an RT statistic that does. The question that would be, how do I put that in a sentence? And this is something you get to practice in your homework. How do I interpret a Pearson correlation between binary variables? So Deborah, where are you? There you are. We talked about this in office hours, right? How do I think about as X goes up and Y goes up when I have categories? It's weird, but not wrong. What you got to know is who's the 0 and who's the 1. As coded in these data, well, who's the 1 and who's the 2? It really doesn't matter so long as you know who's higher. So if we put X as gender and we put Y as marital status, a positive association means as X goes up, Y goes up. So as X goes up means if you're a woman, because women are coded as the 2 and men are coded as the 1, then you are more likely to be high on Y, which means you're more likely to be married. So these 2 numbers right here echo. There's more married women in the sample than is expected by a chance. 171 versus 170. Being a woman is associated with being married to a tiny, 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 tiny extent. Effect size of 0.0004, which is not different than 0. So in interpreting correlations between binary variables, think about what being higher means. And think about if you're a 1 on this variable, a positive association means you're going to be a 1 instead of a 0 on the other variable. If you're a 1 on this variable, a negative association means you're going to be a 0 on the other variable. So high and low have names attached to them, but that pattern still holds. All right. And last question, would Spearman be any different in this case? If I had asked for a Spearman correlation between my two binary variables? What do you think? Yeah, no. Because what Spearman does is rank order them, and they're already rank ordered. So Pearson and Spearman would agree exactly for a binary variable. All right. And same thing in Stata. The only catch is that the expected frequencies in Stata, this is page 10, are only given to 1 decimal place, but the homework system wants them given to 2. So this is one of the very few instances in this class in which I'm going to ask you to calculate something by hand. However, you're going to do it using Stata. Stata will do math for you. So for instance, to calculate the expected frequency to 2 decimal places, it's the row 363 times the column 397 divided by the total. And I asked it to do that with this command right here. Stata is a calculator if you want it to be. So I type display and then I type the equation that I want it to display, and the output will spit out the number. So those of you who are using Stata for this assignment are going to have to calculate expected frequencies to 2 decimal places in order to enter them into the homework system correctly. SAS provides it to the level of precision that's needed. But if you add this to your code, then you have a record of doing these computations and still have something that's reproducible. Okay. And because I like you guys, words. Have some words. All right. That is actually a great place to stop. Not coincidentally because we're out of time, but because the rest of this is talking about type 1 and type 2 errors in power and sort of a different topic. So we'll get to that next time. Where can we find the document that you're sharing now? This document is example 2. It is already posted on the course website on, let's see what day that was posted. Yep, too far. 9/17. The Excel file that I've been typing into is not posted, but will be posted on today's class. Yes, there it is. All right. Any questions before we adjourn? All right, then office hours at 3:15 if anybody wants to say hi. Otherwise, let me know if you need anything. See you Thursday. Bye, everybody.